All right, we've got a new section. We've got 3.10, and we are still talking about derivative rules. I promise we're almost done with derivative rules. This is one of the last sections we're going to talk about here. And we're going to be looking at derivatives of inverse trig functions. So we're looking at derivatives of sine inverse of x or cosine inverse of x. These aren't read as sine to the -1 power. They're read as sine inverse of x. And just as a side note, in other textbooks, other materials online, you may see sine inverse of x written as arc sine of x, and that's simply a different notation. And that would be true for all of these. So if we had cosine inverse of x, you may see that written as arc cosine of x. Simply a different notation, and that trend is going to continue down. So if we're talking about tangent inverse of x, you would see arctangent of x instead. So it means the same thing, it's just a different notation and just sort of a tomato-tomato situation. I do think that the derivatives of these inverse trig functions are a little bit trickier to memorize just because these formulas over here are not quite, they're not as intuitive, I think, to follow. It's a little bit harder to gain reasoning behind them. Luckily for us, they do follow somewhat of a similar pattern here. Notice that the derivatives of sine inverse of x and cosine of inverse of x are almost identical here, 1 over square root of 1 minus x squared and -1 over square root of 1 minus x squared. So we see that they're only off by a factor of -1. The only difference is that negative sign right there in the derivative of cosine inverse of x. And we'll notice a similar pattern for most of these, for the other pairs as well. If we pair up tangent inverse of x with cotangent inverse of x, we'll see again that those derivatives are only different by that factor of -1. Same with secant inverse of x and cosecant inverse of x. Again, the only difference between those two derivative rules is that factor of -1. So luckily, they're all the same. It can perhaps make it difficult to remember when we need that negative sign and when we don't. I don't stress derivatives of these functions all that much. I think there are 3 that are more important, and there are 3 that are, I think, really worth knowing. And those 3 would be the derivative of sine inverse of x, the derivative of tangent inverse of x, and the derivative of secant inverse of x. So notice that these are all sort of the positive cases. We don't have that factor of -1. And they're all sort of half of the pair, right? Sine inverse of x was sort of paired up with cosine inverse of x. Tangent inverse of x, that was sort of paired up with cotangent inverse of x, and so on. The reason these, I think, are the ones that are worth knowing is because they are going to make a really big, important comeback in Calculus 2 if you plan on taking that course. So these are the ones I think that I'm going to be asking about. I don't generally ask a lot of questions like about inverse trig functions on the exam, but if I throw one on there, it will be one of these 3. It'll be of sine inverse of x, of tangent inverse of x, or secant inverse of x. So if you're going to memorize half of them, those are the ones that I would know because those are the ones I'm going to be asking about. One other thing I'll mention is over here we have the domain of all of these functions. So for sine inverse of x and cosine inverse of x, we have a domain of -1 to +1. And that's just because that's the domain of sine inverse of x and of cosine inverse of x. It only accepts x values between -1 and +1. Tangent inverse of x and cotangent inverse of x are a little bit nicer because they have domains of -infinity to +infinity. And then for secant inverse of x and cosecant inverse of x, our domain is absolute value of x must be greater than 1. So these are just the domains of the functions. It's not something that you need to include with your answer when you find derivatives of these functions. This is more so if we were to be working with these functions algebraically. Because the domain, say, of sine inverse of x is restricted, that means that the domain of the derivative will also be restricted. And hopefully you should sort of see that happen, especially right here with sine inverse of x. Let's say if you chose a number bigger than 1, so let's say 2, you would end up with an imaginary number in your denominator. For our class, we're really only working with real numbers, so I think that would sort of pop up naturally. I don't think the domain is going to be anything worth worrying about here in this particular section for our particular class. So let's look at some of these derivatives. I'm mostly interested in practicing derivatives, like I said, of sine inverse of x, tangent inverse of x, and secant inverse of x. And I'm going to be combining these with our other derivative rules. So with our quotient rule, with our chain rule, with our product rule, things like that. I'm mostly interested in, can we apply the derivatives of these inverse trig functions successfully in tandem with those other derivative rules. So let's jump right in. Example 1, I want to find the derivative here of sine inverse of x of 2x squared minus 1. And immediately my attention is drawn to the function that's inside of sine inverse of x. I notice, hey, we have 2x squared minus 1. That is inside of the sine inverse function. This is going to be a chain rule. So if you like to make a note to yourself that, okay, we're using the chain rule here. Chain rule, especially when we're working with these new functions, I always like to go back to the basics, go back to let's really take our time with these problems. Let's go slowly. Let's kind of break it down as much as possible. So I'm going to take my u, my inside function, to be 2x squared minus 1. So u will be 2x squared minus 1, which means that u prime will simply be 4x. So if I make my substitution, I will have y equals sine inverse of u, which is good. Okay, I know how to take the derivative of this function. It's simply given by this formula up here. So I'm looking at 1 over square root 1 minus x squared. That's going to be my derivative. So y prime is 1 divided by radical 1 minus u squared. But again, we're taking the derivative using the chain rule. Remember, every time we use the chain rule, we have to multiply by our u prime right here. So we have our derivative, but it's in terms of u. We want it in terms of x. So we're just going to take our u and our u prime, and we're going to plug that back in. So I should have, let's write that as, well, here, let's do this. 1 divided by square root 1 minus 2x squared minus 1 quantity squared times u prime is 4x. You could leave your answer like that, but I think it's a lot cleaner if you just bump that 4x up to the numerator and say 4x divided by square root 1 minus 2x squared minus 1 quantity squared. Here's my derivative. And you don't need to, I don't need you to worry about simplifying this denominator at all. Sure, you might see some interesting things happen, but for these types of problems in particular, especially because I don't stress derivatives of inverse trig functions, I don't think I'm going to be asking you to simplify these very much, if at all, at the end of these derivative problems. Let's look at another here. Next, I have the derivative. I want to find the derivative of cosine of tangent inverse of x. This one's a little bit trickier, and it's because it's contrasted with part A above. Here I had a chain rule. I had 2x squared minus 1 inside of the sine inverse of x function. When I look at part B here I actually have the inverse trig function. This time I have tangent inverse of x inside of the cosine function. So this might seem a little bit odd, but it is going to be another chain rule. So this is a chain rule. My u this time, though, that inside function is what's inside of the cosine function. This time my u will be tangent inverse of x. And then u prime, okay, let's go look at that. It should be 1 divided by 1 plus x squared. Let me just go and double check. Yep, positive 1 over 1 plus x squared. There's the derivative of tangent inverse of x, so that's my u prime. So if I was to rewrite this derivative, or this expression, in terms of u, this says find the derivative of cosine of u. So, okay, we want the derivative of cosine of u. I know that the derivative of cosine of x is opposite sine of x, so I'll have negative sine of u times, again, I'm using the chain rule here, so I need to multiply by my u prime. So if I take my u into my u prime, plug those back into my derivative that I've just found, I have the opposite of sine of u, that would be tangent inverse of x, times u prime. U prime is 1 divided by 1 plus x squared. And again, we can simplify this a little bit if you really want to. I might say that this is negative sine of tangent inverse of x divided by 1 plus x squared. That's really as simple as it gets. You could pull some really slick math here with your sine of tangent inverse of x. You could actually rewrite that without using any sort of derivative rules, or excuse me, without any sort of trig function if you're really good with your trigonometry. But that's not anything, again, that I'm going to require you to do. It's just kind of a neat little fact, fun fact, if you will. Let's look at a few more examples. Here I have f of x equals secant inverse of x squared. So again, I see x squared inside of the secant inverse function. So this is going to be another chain rule problem where I'm going to pick u equal to x squared. U prime, then, derivative of x squared, will be 2x. So if I rewrite this function in terms of u, I'll have f of x equals secant inverse of u. But that's not my derivative. I want to take the derivative still. So f prime of x, derivative of secant inverse of u. Here I might just need to take a peek here at the derivative of secant inverse of x, and I would encourage you to maybe have these written down next to you as you're working on the homework, just because we will probably need to refer to these from time to time. But secant inverse of x is just a little bit different here this time. It says 1 divided by absolute value of x times the square root of x squared minus 1. So, okay, we'll have, instead of x, we'll have 1 divided by absolute value of u times the square root of u squared minus 1. And again, I'm using the chain rule, right? So anytime I use the chain rule, I need to multiply by u prime. So I have my derivative in terms of u. I just want to take my u and my u prime. We'll plug that back in. Oops, and I'm running out of room. So let's do that right here. We'll see 1 over absolute value of u was x squared, times the square root of u squared, this will be x squared quantity squared minus 1, times 2x. So this is our derivative. This one, I will say, I'm going to show you just how to simplify this a little bit. I don't need to see you simplify your answer in this much detail, but if you're doing problems from the textbook, if you're checking your answer, you might see like, hey, these absolute value, where did that go? It just kind of disappeared in the answer. So I want to talk about why we might simplify this in the way that we would. So here, if you look at x squared, x squared is always going to result in a non-negative number, meaning I can't end up with a negative. So if I take the absolute value of a non-negative number, if I take the absolute value of a positive number or I take the absolute value of 0, I get back the same thing. Which means that if I take the absolute value of x squared, that's actually just the same as just saying x squared. In my denominator, I can also simplify this a little bit more. X squared squared, I have a power raised to a power. I will multiply those two. So 2 times 2 gives me 4. I will have x to the 4th minus 1. And then 1 times 2x, I can multiply those two to get 2x in my numerator. And hey, there's my answer. So you may see your answer written like this. Again, if you were to give me this as your answer, I would be fine with that if you just left it right there. But if you're trying to simplify or trying to see if you got the correct answer, especially if you're using outside resources, you may see some textbooks simplify the derivative quite a bit. Just a couple more here. Here I've got g of x equals e to the x times cotangent inverse of x. So I have e to the x times cotangent inverse of x. I look at that and I'm saying, well, I said times, I'm multiplying those two things. This is going to be a product rule. So if I want to apply my product rule here, let's look at this g prime of x. First, I'm going to take the derivative of e to the x, but of course, the derivative of e to the x is just e to the x times cotangent inverse of x. That part stays exactly the same, cotangent inverse of x, plus, now I'm going to leave e to the x alone, so that part of my function stays exactly the same. And I'm going to multiply that by the derivative of cotangent inverse. So the derivative of cotangent inverse should be negative 1 over 1 plus x squared. Let me just double check that I have that correct. I want derivative of cotangent inverse. Yep, negative 1 over 1 plus x squared. So there we go. There's our derivative. Again, I would probably just leave my answer like this. If you really wanted to, sure, we could factor out an e to the x, and we could say, well, this is e to the x times cotangent inverse of x plus negative 1 over 1 plus x squared. You could get a common denominator if you really wanted to, but I think that's probably a good place to stop for that problem. Let's look at one more example here. This time I have y equals cotangent inverse of x, cotangent inverse of e to the x divided by x. This one's tricky because we actually have two different derivative rules occurring here. I have, first of all, I see a chain rule because I see this e to the x divided by x inside of my cotangent inverse function, so it's absolutely going to be a chain rule problem. But then I see this piece right here, and I think, well, when I go to take the derivative of that inside part, go find my u prime, I'm going to have to use the quotient rule on that guy. So this is a chain and, a quotient rule problem. So let's start with our chain. I think that's probably where I would begin, and I would say, okay, I know that this is going to be my u. I have e to the x divided by x. U will be e to the x divided by x. U prime, the derivative here, let's see, I'm going to need my quotient rule, so that says low, so that'll be x. D high, derivative of e to the x, that'll just be e to the x, minus high, so that's e to the x, d low, derivative of x, that's just 1, square the bottom, away we go. So I'm left with x times e to the x minus e to the x divided by x squared. If you wanted to, you could factor an e to the x from the numerator. I'm not going to, though. I think I'm just going to leave that as my u prime. So, okay, we've done our quotient rule at this point. Now that part's done. I have to get back and finish my chain rule now. My chain rule says, okay, let's rewrite this as a function of u. So y equals cotangent inverse of u. So the derivative of that y prime, we just said derivative of cotangent inverse was -1 over 1 plus u squared. But again, we're using the chain rule here, so we need to remember that we have to multiply by u prime. And then I just need to substitute my u and my u prime into this derivative. So y prime equals -1 divided by 1 plus u squared. Well, what's u? U is e to the x divided by x. Oops. So I have 1 plus e to the x divided by x, quantity squared, times u prime. Well, u prime is this whole big derivative that we found using the quotient rule. So times x e to the x minus e to the x divided by x squared. We could simplify this a little bit, but to be honest, at this point, we've already used our two derivative rules in the quotient rule and the chain rule. I think that this is as good a place as any to stop. So I'm just going to say, you know what, that is our derivative. So the one word of warning I will give you is if you don't plan on simplifying your derivatives, like if you had planned to leave this as your answer, be very careful when you're typing your answers into MyMathLab. You kind of have to have it exactly just right. If you miss parentheses or if you miss your fractions or something like that, it is really easy to slip up and make a mistake. So just double check your answers before you type those in if you're not simplifying your derivatives.